Okay, so come to one of the major applications of complex analysis at this part of the course, right, which is calculation of integrals. Integrals via residue calculus. So there's a bunch of standard problems to cover here, yeah? And so last class I showed you how to do like integral of a, rational function of sine and cosine. You can make a certain substitution and convert it to a integral around the unit circle, right? And then you can calculate that integral by finding singularities of the corresponding rational function in z. So this time I'm going to describe a pretty common other type of problem, which is if you're integrating something like, well, let's see here if I can say it this way. Well, actually, I just need to set up, basically I want to talk about the half circle residue. All right, so if I have residue, let me curve. So a curve that looks like this, basically. All right, so let's say this is going from minus r to r like that, right? And then you've got this half circle counterclockwise up here. All right. So I'll call this curve altogether. Here's the notation. I'm using CR for the half circle up here, and this guy down here is minus r to r, right? Remember, we have a sneaky notation that the closed bracket from complex number to complex number is the line segment from those points, from one point to the other in that direction, right? Okay, so if we're going to consider D to be the interior of this, right? Then the boundary of D is what? It's minus r comma r union with that half circle, right? And so if we have a function, right, which is analytic at all but a finite number of isolated singular points, z1 through zk, in the disk, right, what can we say? So if you got singularities like z1, z2, zk, what's the result? We know Cauchy's the residue theorem, right, says that the integral over the boundary of D of f of z dz is equal to what? It's equal to 2 pi I some, let's say j equals 1 to k of the residue of f of z at z sub I. I mean z sub j, right? So this is how we can calculate the integral around the boundary of D. But of course, we can also break this into two pieces, right? So what we're really looking at is the integral from minus r to r, right? F of z dz, plus the integral over CR of f of z dz, f of z dz, equals to 2 pi I, sum of the residues, right? Okay? So then the trick is this. If we're dealing with a function, right, that as r goes to infinity, right, if the modulus of f of z, right, is less than, let's see here to be greedy, m over r squared for, r greater than, some particular radius, right? So if the modulus of f of z eventually gets smaller than say m over r squared, then what do we have?
The ML theorem.
The ML theorem, right? Yeah, then the integral over CR of f of z dz, the modulus of that, right, is less than or equal to m over r squared. What's the length of it?
The length of the half unit circle.
Yeah, length of the half circle is what? Just not 2 pi r, but just pi r, right? And what do you got there? You've got m pi over r, right? So as r goes to infinity, in this context, what happens?
As r goes to infinity?
Yeah.
It goes to 0.
So as r goes to infinity, we obtain that the limit as r goes to infinity, right, of the integral from minus r to r. And I should be careful here. I said minus r to r, but I meant to write here, guys, minus r to r, like, I mean, this, so it's the integral over that path, right? But what is that path? That is just z equals to x, right? So dz is equal to dx for that line segment, yeah? So this guy has z equal to x for minus r less than or equal to x less than or equal to minus, yeah, minus, words. Minus r less than or equal to x less than or equal to r, and dz is equal to dx, right? So this literally is the integral from minus r to r of f of x dx, right? And that is equal to, well, 2 pi I times the sum of the residues, right? Where's the other term? It's gone in the limit, right? Because those pieces are killed off by the ML theorem. If we can bound the function like that, yeah? So when can you bound a function like that? Here's an example. If we have a rational function, right, f of z is p of z over q of z, where the degree of q of z is greater than or equal to the degree of p of z plus 2, all right? Then you can make this kind of bound happen. Let me remind you how that all goes. It's a little fussy. So let me suppose here q of z equals to an z to the n plus plus a2z squared plus a1, yeah? A1z plus a naught. And let's see here. I showed that there exists an r greater than 0 for which q of z is bounded below by a sub n times r to the n over 2 for z greater than r. So this is bounded below. How can I say that? Let's say you can argue that q of z is greater than or equal to the modulus of a sub n over 2 r to the power n for modulus of z greater than r. That's not easy, actually. That's the kind of tough part, right? So we come up against this in a homework problem before, and I have a solution included in one of your previous homework, so I don't want to like rehash it in class. It's a little bit sneaky how that's done. So like I said, it's on page 131 in Churchill, and it was in problem 44 of the homework when I wrote these notes. Which problem it is in your homework, I'm not precisely sure, but anyway, I'll just say that, okay? I'll try to work out the details for like the actual problems we work, but this can be proved. And once you have that, right, if P of Z is equal to, say, you know, B, what would it be? If the degree of Q is greater than or equal to, well, whatever the degree of n minus 2, that'd be the largest possible power, right?
Yeah.
Z to the n minus 2 plus da 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 plus B, B1Z plus B naught, then the modulus of P of Z is what? It's less than or equal to B n minus 2 R to the, oh, excuse me, I got a modulus here, right? Modulus of this times the modulus of Z to the n minus 2 plus da 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 plus. So this is by repeated application of the triangle inequality as well as the just properties of the modulus, right? But so here, where am I looking at? This whole discussion is for Z, for the modulus of Z greater than R, all right? For some particular R that's supplied by arguments I'm not quite giving you here, right? But like I told you, if you look at page 131 of Churchill, you can find the explicit argument there. This is less than what? So this is modulus of Bn minus 2 R to the n minus 2 plus da 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 plus, you know, modulus of B1R plus modulus of B naught, right? And so what we have then is that the modulus of f of z is equal to, what was less than or equal to what? The modulus, all of this stuff here. I make the words here. So modulus of P of Z over the modulus of Q of Z, right? But we can make the numerator larger by replacing it with all this, right? And we can make the denominator smaller, right? Which makes the fraction larger by replacing it with just what? Modulus of an r to the n over 2, right? And while that isn't of the form m over r squared, right? It's not quite that. It will behave the same as m over r squared in the limit of the ML theorem. So then the integral of f of z dz for such a rational function over the half circle of radius r of r sufficiently large, right, is going to be less than or equal to pi r times all this stuff, right? So 2 pi r, and I'll just go ahead and do the reduction. You got, you know, modulus of bn minus 2 r to the what? Minus 2 plus what? Plus eventually you get modulus of b1, you know, 1 over r to the n, modulus of b naught over r to the, and I think I've, yeah, r to the n. And you see what happens if you multiply through the r. What do you get? Multiplying through the r, if you don't mind me, I'll just make the correction like this. I get a minus 1 here all the way down to n plus 1. This should be n minus 1 there. So that's just r. This is actually already correct. It should have been n minus 1 before I made that step. My point to you is after you cancel the r out, you're left with what? constants and reciprocal powers of r, what happens as r goes to infinity? All of that goes to 0, right? And as r goes to infinity, certainly that's also the case where we're able to insist that the modulus of z is greater than whatever r is needed for this technical estimate here. Yeah. So anyway, long story short, that means that we can apply this technique to do an integral of any rational function of complex variables where the degree of the numerator is 2 degrees less than the degree of the denominator, or more. Yeah. Any questions?
No, I didn't read the second one for a little bit. I think you can. Because I was like, is that true that, and like the limit of, let's say, like power, and then like you add up all those sequential powers, like x to the third plus x squared plus x plus 1 over x to the fourth. That goes to 0 as x goes to infinity. I was like, I don't know if I believe that on for.
Well, here there's finitely many terms, right?
Yeah,
And yeah.
I knew it was finitely many terms, but I think you can prove that with just like a L'Hopital's thing.
Oh, you want to think about this in terms of L'Hopital's? I mean, that would not be unreasonable. It is a real fraction of r.
Yeah.
R is a real variable. You could use L'Hopital's rule here reasonably to calculate the limit, sure.
Yeah. Because I didn't, like, I was like.
How many races? Okay.
No, you didn't. I wasn't like convinced that limit fraction.
Yeah. What's interesting is you can also deal with integrals of rational functions where the degree of the numerator is just one more than the degree of the denominator. Mm-hmm. If it's multiplied by like a sine or a cosine, something nice happens there. There's something called Jordan's lemma, which hopefully we'll look at. Maybe not today, but sometime soon. Let's see here. So, an example. I'll start with an easy one, which we could do this calculation in Calc 2 just the same, right? Let's calculate the limit as r goes to infinity of the integral from minus r to r of dx over x squared plus 1. All right. So this is going to be equal to 2 pi I times the residue of 1 over z squared plus 1, where? So we need to think about this. So what we're doing is we're applying the general discussion I just did, right? We're thinking about f of z. So we're going from minus r to r, right? And we've got our half circle CR again. And the question is, so our f of z is what? Apparently 1 over z squared plus 1, right?
Yeah.
What are the singularities of that? Yeah, minus I.
I think only minus I. I mean, only I really is concerned.
Exactly. So the only isolated singularity inside the upper, semicircle, upper half circle rather, as r goes to infinity, doesn't matter how big r gets, it's still just I. I is the only residue we have to consider, right? So, and then how should we calculate that residue?
What is it? I would do the rule 3 rule, or the special case rule 3.
Special case of rule 3 or rule 4 even, right?
Yeah.
So it's differentiate the denominator, which is giving me 2z, and then I'm supposed to evaluate the residue. I mean, at the singular point is equals I. So I get what? 2 pi I over 2i, which is
2 pi.
Just the 2's cancel though.
Oh yeah, pi.
So we just get pi. Now, technically speaking, I should mention to you guys, what we're calculating right now is the principal value. I don't know if you've ever heard of this, probably not. The principal value of the integral from minus infinity, this marker's dead. So the principal value of the integral from minus infinity to infinity of f of x dx, yeah? What that is literally the limit as r goes to infinity of the integral from minus r to r of f of x dx, okay? When the integral from minus infinity to infinity exists, it's equal to the principal value. So this is equal to the integral from minus infinity to infinity of f of x dx when this exists. Now, how do you decide if the integral from minus infinity to infinity exists? How could it not exist? And yet the principal value exists. Do you guys know? What's an example of an integral whose principal value exists and yet the integral doesn't exist? How about this? X dx. The integral of x from 0 to infinity pretty clearly diverges, right? I mean, it diverges from both sides.
Yeah.
But this would be the limit as r goes to infinity of the integral from minus r to r of x dx. But this is an odd function, integrated about a symmetric interval of the origin.
Yeah.
So that integral is just straight 0. And the limit of 0 is 0, no matter if it's going to infinity or what.
So why would we have indefinite intervals? Does it work out? Like, is that just like a definition of indefinite interval?
What is the definition of an indefinite integral? An improper integral?
Yeah.
So the definition of improper integral from minus infinity to infinity of like f of x dx is equal to the integral from whatever, I'll just use 0 to infinity of f of x dx plus the integral from, I should really start with minus infinity. Minus infinity to 0 plus the integral from 0 to infinity of f of x dx. And these, it's not that those cancel here.
Yeah.
Neither of those exist for the principal value I just considered.
Yeah.
But the issue is that this is the limit as, let's say, s goes to minus infinity of the integral from s to 0, f of x dx, right? Plus the limit, let's say, if t goes to infinity of the integral from 0 to t of f of x dx. Notice that the limiting process at infinity and the limiting process at minus infinity, they're completely divorced in calculus 2. This is our definition of integral from minus infinity to infinity. The infinity and the minus infinity, they're not in any way coupled. But with the principal value, they are. The principal value is the limit taken symmetrically to infinity. So it's a very different animal than this in principle. Now in practice, they can match up. If it happens that this exists, then they'll be equal.
Yeah.
So a lot of times in this course, I just give students free license to assume that the integral exists because it makes it more fun. So like this one. And of course, how else could you have done the example 1 without complex analysis? What would you have done? It's not complicated, right? The integral of dx over x squared plus 1 is inverse tangent of x, right? Plus a constant. So if you calculate the, you end up with, so if I can use some engineering notation for a moment here. Basically, the answer is inverse tangent of infinity minus the inverse tangent of minus infinity, which is pi over 2 minus a minus pi over 2. Now, what I've just written is mathematical heresy, but you will find this kind of thing written in engineering courses. Yeah, that's a shorthand for taking the limiting processes I just wrote above. One going to minus infinity, one going to infinity, respectively, giving me the limits of pi over 2 and minus pi over 2. Because them's the horizontal asymptotes of the inverse tangent. Because the vertical asymptotes of the tangent flips the horizontal tangents. We look at the inverse function. That's Calc 2. All right, so let's look at a more interesting example. What's that? Uh-oh. Are you thinking about the GRE? Oh, I see. Well, I guess since they're not offering it again, we could talk about it, but example 2. I know you're sworn to not talk about it. I hate those disclaimers you have to write. I hate the legalese they make you sign at the start of that thing. It's so obnoxious. Like, I want to talk about this thing to people. Don't make me sign away my life to not talk about this thing ever again.
I signed it in pencil.
You signed it in pencil? Yeah. Were your fingers crossed?
Yeah.
So we're going to look at this one, and we're going to use this guy to calculate the integral from minus infinity to infinity of, well, excuse me, we're going to calculate, I'll be careful here. Integral from r to minus r. I would argue that, in fact, this one, the limit exists. And to see that the limit exists, you could go to some of the, there are arguments we have in Calc 2 to see integrals, improper integrals exist in terms of comparison to other known integrals and such. And I'm sure you could give that kind of argument here if you were so inclined. So here we have integral of dx over x to the fourth plus 1 limit, from minus r to r. How can I calculate that integral using complex analysis? Well, this time, right, I am thinking about, again, what contour am I using? I'm using the half circle contour, right? And I need to think about f of z equals 1 over z to the fourth plus 1, right? What are the singularities of this? Well, they're the fourth roots. We're looking for where z to the fourth plus 1 is equal to 0, right? So that's to say z to the fourth is equal to minus 1, which is to say that z is what? Is an element of the fourth roots of minus 1. Right?
Yeah.
So what are those? So we can calculate the principal fourth root of minus 1. So that's e to the what? That's the principal fourth root of e to the pi minus I pi over 2, right? Which is e to the minus I pi over 8, I believe. Check it out. E to the minus I pi over 8. Raise that to the fourth power. What do you get? You get e to the minus I pi over 2, right? Which is minus which is minus 1, right? So I get that one, and then what are the other, so where is that? It's a little bit below the axis, right? So that's like down here somewhere, right? Let's say here. Let me call it z1 equal to e to the minus I pi over 8. That's my first singularity. And then we're looking at fourth roots, right? So we can just take that and rotate by 90 degrees to find the next one. So like the next one's up here, right? And then there's another one over here. And then there's another one down here. So this would be z2 equal to I e to the minus I pi over 8, right? And this guy down here is z3 minus e to the minus I pi over 8, yeah? And z4 I don't really care about. The point to this is that if we can argue that the modulus of f of z, right, we can prove that this integral back over here on the other board, that the integral of over CR of f of z dz vanishes as r goes to infinity. I think we can do that, right? Because I mean, this one, let's make this one explicitly. Can you explain to me how 1 over z to the fourth plus 1 can be bounded? What's a bound on this? This is less than or equal to what? 1 over what? Absolute value of the modulus of z to the fourth minus 1, right? So what I did there was I let the absolute value, and the modulus of the denominator become something smaller, right? Do you remember this inequality we have?
The inequality of a plus b is less than.
Yeah, I'll use z and w here for a second, but like modulus of z plus w is greater than or equal to the absolute value of the modulus of z minus the modulus of w, right? So putting that into practice over here on the denominator, I get that, right? My point to you is we don't need the fancy technical lemma for this problem. We can pull our own weight on the estimate for this problem, right? And the same was true for example 1. I wanted to show you, like, indicate the general result start class, but I also don't want you to have to rely on that necessarily. So like we can show these details. Here they are. What is this? This is equal to 1 over r to the fourth minus 1 if what? If modulus of z equals to r is greater than 1, right? You just need to have bigger than the unit circle for your half circle, and you've already got the estimate that you need. And then as r goes to infinity, you see that the integral is bounded by like pi r over r to the fourth minus 1, which goes to 0, which just leaves us with, again, going back to the calculation that started class, the limit as r goes to infinity of minus r to r is equal to the residue, 2 pi I, residue of what? Yeah, so that's 1 over z to the fourth plus 1. Yeah, e to the, I e to the minus I pi over 8.
Plus residue.
Yeah, plus 2 pi I res of 1 over z to the fourth plus 1. And then minus, right? E to the minus I pi over 8. Again, I think rule 4 is the way to go here, right?
Yeah.
So what you got? You got, I'm going to put it down here, equals 2 pi. Yeah, we put up 2 pi out front?
Yeah.
Okay, so you got 1 over 4z cubed, right? So we're going to do I e to the minus I pi over 8 quantity cubed plus what? Plus 1 over 4 minus e to the minus I pi over 8 cubed, yeah? So we can factor 4 out, right? Bringing the 4 out front, we get what? We get pi I over 2. And let's see, what's I cubed?
I cubed is minus I.
So we get minus I, and then e to the minus 3 pi I over 8, right? Plus, or rather I should say minus 1 cubed is minus 1, right? So I get minus 1 over e to the, again, minus 3 pi I over 8. So it looks like I get pi I over 2 times, I can rewrite that as I minus 1 times e to the 3 pi I over 8. This,
Well, oh, wait, but
oh, I'm an idiot. I'm a dummy. Look at this. Is minus 1 equal to e to the minus I pi over 2? Why do I have notes out if I'm not going to look at them, dummy?
-1.
What is this? Help me out, guys.
Oh, that's e to the I pi.
This is cosine pi over 2, minus pi over 2, right? Plus I sine of minus pi over 2, which is what? It is minus I. In other words, sorry. So what do we have to do to fix this?
E to the minus I pi.
E to the minus I pi is what I didn't need the 2 there, did I? In fact, I didn't need the minus either, right? So what we should have had is e to the I pi. E to the I pi is equal to, I mean, good to ask, cosine pi plus I sine pi, right?
Yeah.
Which is minus 1 plus I times 0.
Yeah.
So that's minus 1.
But minus 1 to the 4th is not. See what I'm saying?
Well, the fourth root of e to the I pi is what?
4 pi I.
Is
I mean, sorry, e to the I.
e to the I pi over 4, right? So let's try this again. I mean, the bound argument's still fine. Hooray! So e to the pi. So the singularities are, the one of them's at 45 degrees here, right? E to the I pi over 4, but then the other one's over here at I e to the I pi over 4. And then, of course, the two we don't care about are down here and here. Minus e to the I pi over 4 and minus I e to the I pi over 4. Those are the fourth roots of minus 1. Only one of which, right? Excuse me, two of which are within the contour we care about. So yeah, we need to be careful about this calculation. Otherwise, we will pay the price of miscalculation and having to redo what we started doing. But we'll get it. This is the silver lining here is now that we've corrected it, it'll be easier to calculate. So we've got e to the I pi over 4 and I e to the I pi over 4. All right, so we'll factor 2 pi I out like you did, right? So we got 1 over what, 4 e to the I pi over 4 cubed, right? Plus 1 over 4 e to the I pi over 4 cubed. I think I lost my I. Okay. So we get pi I over 2, right? Yeah. And that gives us a 1. Let's see, that 1 over I cubed, right? On the other one is minus 1 over, so that's 1 plus I times e to the minus 3 pi I over 4, yeah? But what is 1 plus I? Like the easy way to do this calculation is actually put 1 plus I back in terms of polar coordinates. What is 1 plus I in terms of polar coordinates? 1 plus I,
That's the 45 degree.
right, it's square root of 2 times e to the I pi over 4.
Yeah.
Right, so this gives me pi I over 2 root 2 e to the I pi over 4 e to the minus 3 pi I over 4, which gives me pi over root 2 times I pi over root 2, excuse me. And
That gives you minus pi I
So this is e to the, what did you say, e to the minus pi I over 2?
Yeah. Pi over 2.
And as we were, hey, here, we're back to that again, but now for the right reasons.
Yeah.
So that's minus I, right?
2 go.
Where did my 2 go? What's root 2 over 2?
What's root 2 over 2?
Yeah.
I see.
So I think if I haven't made yet another mistake here, I believe we get pi over root 2. I'm scared to look at my notes. Okay, pi over root 2. Whew. This was example 7.2.3 on page 148 of my notes if you're curious. All right. Now, for those who aren't faint of heart in calculus 3, you can calculate that integral by brute force calc 2 methods. Yeah? But I don't recommend it. All right. So I have the stone cold like antiderivative courtesy of Wolfram Alpha in the notes if you want to look at it, but it's kind of beastly, isn't it? All right, so let's try to do another example here right quickly. So example 3, and so this is the one we'll need the Jordan lemma for, which perhaps I'll prove another day, but not today, obviously. So it's essentially the same picture again here, but this time we're going to consider f of z equal to e to the I a z over z squared plus 1. Right, so it has singularities where?
I.
Yeah, plus or minus I, right?
Yeah.
Now I is the relevant one. Very good. So if we look at the half circle like so, yeah, from minus r to r, CR, we just have the singular point here and here, right?
Does hitting e to z not change it?
And the thing is, the modulus of f of z, right, is equal to the modulus of e to the iaz over the modulus of z squared plus 1, yeah? And what's the modulus of that? Well, I think it's a little fussy, isn't it? Because if A is, I'm assuming A is real here, I suppose. Let's suppose it for A greater than 0. Okay, real. What is this?
Scalar.
Is it though? Because e to the I a times x plus iy is what? E to the I ax minus ay, right?
Yeah.
So this is actually equal to e to the minus ay over the modulus of z squared plus 1.
Why are you only considering the AI portion?
Well, the e to the IAX piece has modulus 1.
Oh, yeah.
So when I take the modulus of that, the e to the IAX piece drops out. But anyway, our time is limited, but it turns out you can argue that the integral over the half circle piece of this again vanishes. And so what we get is the limit as r goes to infinity of like the integral from minus r to r of, and so what happens when you evaluate this function at z equals to x? It just becomes e to the iax dx over x squared plus 1, right? Well, that's going to be equal to 2 pi I times the residue of e to the iaz over z squared plus 1 at where? At I, right? And it seems like this is a job for rule 3, right? Rule 3 is the way to go here. Simple pole, 2 pi I. So we evaluated I, right? E to the iai over differentiate the bottom, right? So 2z, which is just 2I here. So what we get the 2's cancel, the i's cancel, and we've got pi e to the what? Pi e to the minus a, right? And so what does this tell us? What is this one over here? Well, if you'll allow me this slight jump, the integral from minus infinity to infinity of both the real and the imaginary part exist, okay? And so this actually gives you the integral. What is e to the iax? It's cosine ax, right? Plus I sine ax, right? So this is straight up integral of cosine of ax dx over x squared plus 1 plus I times the integral of sine of ax dx over x squared plus 1. Minus infinity to infinity, minus infinity to infinity. Again, I'm assuming that the principal values of those integrals are equal to the integrals, right? And what is this? What can you read from this calculation? This is equal to that, right? So what does that tell me about the integrals? It tells me two things. It tells me, one, that the real integral, it tells me that this integral is pi over e to the a, and this integral is 0. Anyway, I have some more supporting inequalities in the notes on page 149 if you're interested. So I think that's it for today. We will continue. There's many more tricks to learn here, as I will show you in the next couple lectures, I think. So thanks, guys.